All right. Hello, everyone, and welcome to Design It Day. In this particular session of Design It Day, Atsuko Hoffman will be taking us through some of the challenges and intricacies of designing passive components into DC to DC converters. We'll take a look at the various options, some of the trade-offs, and then what happens when you trade off certain elements in picking one component type over another. Before we get started, I'll introduce myself. I am Wilmer Compagnoni, and I lead the technical marketing team at Chemet. And as I said earlier, with us today is Atsuko Hoffman. She's an FAE, a field applications engineer, based out of our offices in California. Before I hand it off to Atsuko, just want to let everybody know that you are muted upon the entry into the session. And if you have any questions, please submit them through the Q&A portion of the Zoom window. And as soon as Atsuko's done, we'll address any questions that came in time permitting. If we don't have time to get to your questions, you can still submit them through a form that we'll show later, and then we'll address those questions at that time. So without further ado, I'd like to hand it off to Atsuko. Atsuko, at your pleasure.
Thank you, Wilmer. Hi, everyone. My name is Atsuko Hoffman, and I am a field applications engineer out of California. Here you go. A little bit about myself. I graduated college and I have been working in this industry, passive component industry and semiconductor industry about 20 years or so. I did some work in component design and in quality group. And I did some work in business management, product management. And in the last 5 or 6 years or so, I have been in technical sales and in field application engineering role. I have been with Chemet for about 3.5 years. And I love field application engineering because I get to exposed to many different applications. And I learn something new every day. With that, let's move on to today's agenda. We are going to cover DC to DC converter basics that includes a buck converter and a boost converter. And then we go through how the inductance is determined in DC to DC converter circuits and the different inductor choices. We do the same for capacitors. We go through how the capacitance is determined and the different capacitor technology options. As we go through these, we will introduce simulation tools that is web-based on our Chemet website, and introduce that so that the designers can see, what's available and what kind of component parameters are available and so on. And that helps designers to design the DC to DC converter circuit. And then we will close with key takeaways. And if we have time, we do a Q&A. So what is a DC to DC converter? A DC to DC converter is a type of converter switching regulator, and it converts one type of DC to another. It takes input voltage that may have some variation and produce a stable output voltage. It can be either step down the voltage, a buck converter, or step up the voltage, a boost converter. And in addition to generating output voltage, a good DC to DC converter maintains a stable output when the load current changes. It also should have a good transient response that can minimize settling time, overshoot and undershoot of the output waveform when there is a sudden fluctuation on the load. DC to DC converter come in many different topologies, but active elements, the semiconductor part, usually work with the passive elements such as inductors, capacitors, and resistors. Here we have two configurations. The top one is a simple buck converter. It takes input voltage and step down the voltage to generate output voltage. So the output voltage is smaller than input voltage, and the output current is larger than input current. The bottom configuration is a boost converter. It takes input voltage and it steps the voltage up to produce output voltage. Output voltage is larger than input voltage, and the output current is smaller than input voltage, input current. That's because the power going into the system needs to be equals to power going out of the system, from the system, as we all learned at school. And then these buck converter or boost converters, they both use inductors and capacitors, and the inductors control the current and store the energy by creating the magnetic field and collapsing the magnetic field. For capacitors, capacitor generates the output voltage, and it filters it, and then it creates stable output voltage. In order to run a DC to DC converter, the specific operating parameters are what determine the values of the passive components. Here we have a simple buck converter configuration, and operating parameters such as input voltage, output voltage, switching frequency, and so on are listed out. Using these values, these numbers, and then you plug these numbers into this equation, you can get a target inductance that works for this particular buck converter. And in this case, it is 40.44 microhenry. But 40.44 microhenry will not work in the real world because no vendor produces this specific 40.44 microhenry inductors. So your choices are, you can either go down the inductance from target value 33 microhenry, or you can use higher inductance value, 47 microhenry compared with the target value. Using the lower inductance would make the ripple current higher, a little bit higher. Using the higher inductance than target value would lower the ripple current a little bit. And of course, there are some choices for designers, either ferrite, you can use ferrite inductor, or metal composite inductor. There is no such a thing as one inductor fits all, unfortunately. And here we have metal composite inductor and a ferrite inductor listed out. And sometimes application itself may determine which inductor to use, which is suitable, but we go through each pros and cons in this slide. As you can see, there's a graph on the top. Let me see if I can laser pointer. Okay. On the graph on the top, inductance versus current, you see the yellow line. This is the profile, inductance profile for metal composite inductor. Metal composite inductor has very good performance because it's got what we call soft saturation profile. Soft saturation meaning if you increase the current, and then usually the inductance start decreasing here. But with soft saturation profile, you increase the inductance, but the change in inductance is very small. It's a gradual change. So that's what we call soft saturation profile. So therefore, we have a high saturation current capability in the metal composite inductor. And if you can look at this graph, the solid line is for the room temperature data, and then the dotted line is for the high temperature data. And as you can see, there's not much change in inductor performance between room temperature and high temperature. So those are the good things for metal composite inductor, but there are some drawbacks in metal composite inductor. It is related to the material itself, and the metal composite inductor material does not have as high permeability as ferrite inductor material. So that limits kind of, making the large inductor in small sizes. So these are the drawbacks. Now let's take a look at ferrite inductor right here. On the graph, it's green line and a green dotted line. Like I said, ferrite inductor has high permeability, so you can make larger capacitance in small size. And if you take a look at the saturation current, saturation point, I would say right here, or right here, around here, below that saturation point, inductance is very, very stable. You don't see much change in inductance up to the saturation point. So these are the benefits for ferrite inductors. However, there are some drawbacks as well. And as you can see, the saturation point right here at room temperature, and then saturation point at high temperature are different. That's because it has the harder saturation profile and the material dependent. So you can, you would see the saturation point at higher temperature is lower than the room temperature. So that's a drawback. Now, in most applications, loads are not constant. You see the light load, mid load, and then heavy load, and then you may move back and forth in your application. If you're using ferrite inductor that has a hard saturation profile like this, and if you are using the inductor at saturation current region, the changing current may result in inductance drop. And then the inductance drop may be quite a bit. In this example, when you change the load current from 1 amp to 2 amp, you would see inductance drop from about 40 microhenry down to 30 microhenry. So that's a 10 microhenry difference when you change the load from 1 amp to 2 amp. What that means is that it may be the target inductance may be falling short, and it may result in increase of output ripple. On the other hand, if you look at metal composite inductor, it has soft saturation profile. So when you change the current from 1 amp to 2 amps, the inductance change is very minimum. It's not as much as the ferrite inductor. And what that means is that you can stay closer to target inductance value, and then you may not see as much as ripple increase like ferrite inductors. Now, inductors are known to heat up during its operation. Temperature rise in an inductor is defined as total power loss multiplied by coefficient of thermal resistance of the component itself. And total power loss has 3 major elements. It's a sum of DC loss in copper wire, AC power loss from copper wire, and magnetic loss in the core. I have a detailed slide on the next, but the losses have a dependency in the amount of output current. As the output current increases, the copper loss starts dominating the loss. And here, if you follow this link, this is our KSIM tool link, and you can get kind of estimate the sense of how much temperature rise that 1 or 2 particular components have. And this is a screenshot of KSIM, and you can see the temperature rise versus the current. And then you see the two inductors profile here. And then you can change the condition, maybe switching frequency or current condition, and then you would see different temperature rise profile. So it's a useful tool. And then we also have a YouTube video clip that explains what RMS current is in an inductor, and what is the temperature rise of the inductor. And then it goes through those temperature rise of the inductor. And it's really easy to understand. Now, we talked about power loss a little bit. And here, we have a little bit more detailed explanation on the total loss versus output current profile. As you can see, the lower current region, like 1 amp, 2 amp, and then 3 amps, the core loss, the blue portion, blue one right here, is the dominant factor of the power loss. But as you increase the current, you would start seeing more and more of copper loss contributing into the power loss. And at high current situation, and especially at high frequency situation, the copper loss, AC copper loss, the skin effect is getting more dominant. And then so most of the power loss is coming from copper loss at high switching frequency situation. Now, the third element of the power loss was from the core, what we call core loss. And the core loss is strictly related to the material we use. In this case, we're showing ferrite, manganese, zinc ferrite material core loss. And then the metal composite, it is an iron silicon base materials core loss. As you can see, like for example, at 1 megahertz, the ferrite core loss is a lot lower than the metal composite core loss. And then the ferrite inductors core loss is very low in wide frequency range. We talked about a lot of inductors, but here is the summary. In this table, we have design parameters or design constraint, current, frequency, size, and so on, and then suitable solution or suggested solution, either metal composite inductor or ferrite inductor. But each solution has trade-offs always. So we kind of put the table together so that the designer can take a look. And this is not a Bible, but it's a guide to navigate which technology to use in the DC to DC converter circuit. For example, if you take a look at size, if you have a size constraint, you have tiny space on the board, maybe the ferrite might be the better solution over metal composite inductor. However, you may have to sacrifice for the current. The ferrite inductor has hard saturation profile, so you have to watch out for the saturation region, the inductance change in saturation region. And remember, there are some temperature dependency on the saturation point between room temperature and then a high temperature. So you have to watch out for that. So these are the drawbacks. So it's always, there is a pros and then there's a cons. Now we're moving on to capacitors. You may think that choosing inductor may be tricky and choosing capacitor may be easy. In reality, it is not that simple. Here we have the same buck converter configuration as we just went over for inductors. You can see the same design parameters, input voltage, output voltage, switching frequency, this and that. When you plug these numbers into this equation, you can get minimum required capacitance, 30.8 microfarad, and an ESR maximum 20 milliohm. You have choices of using different type of technology capacitors. We put 3 examples here. One piece of 47 microfarad X5R, 2 pieces of 22 X7R MLCCs in parallel, and then 1 piece of 33 microfarad tantalum polymer capacitors. And different capacitor has different effect on ripple voltage waveforms. Here we have ideal capacitor, MLCC, and then polymer, tantalum polymer capacitors ripple voltage waveform. And then there's no such a thing as ideal capacitor always. So in real capacitors such as MLCC and polymer capacitor, there are some parasitic element, such as ESR equivalent series resistance. When you introduce ESR to the capacitor, you would see a little bit of overshoot and undershoot. In addition to ESR, it has ESL, equivalent series inductance. And when you introduce that, the waveform, you can see further overshoot and undershoot. And for MLCC class 2 capacitors such as X5R and then X7R, there's a DC bias effect. So it affects the ripple voltage waveform further. And for tantalum polymer capacitor, it's got a cap roll-off effect. Capacitance get smaller, lose capacitance at especially very, very high frequency operation. And it affects the ripple voltage waveform as well. And then here we have a project. You can follow this link to see the YouTube video, but we have TI buck converter, TI's buck converter evaluation board, and then we used different capacitor technology, tantalum polymer capacitor, MLCC, aluminum polymer capacitor, the CAN type, and then aluminum polymer type capacitor, the chip type capacitor. And then you can see the ripple waveform is different depending on which technology you use. And just like inductors, capacitor has trade-off as well. For using 2 pieces of 22 microfarad X7R capacitor, it's a good solution. It's got low ESR. MLCC has the lowest ESR among different capacitor technologies. And it can operate in wide temperature range. X7Rs are rated from -55 to 125. But the drawback is that there is DC bias effect, and you may have to use multiple capacitors to hit certain target capacitance value for your DC to DC converter. X5R, it's a good solution too. It's got a higher dielectric constant value compared with X7R, so that the capacitance is a little higher than X7R. And we offer small case sizes as well. But the operation temperature for X5R is between -55 to 85 degrees C. So you don't have, 125 degrees C operation like X7R. So you have to sacrifice that. For tantalum polymer capacitor, it's got highest volumetric efficiency in capacitance. So we offer high capacitance, and then there is no DC bias effect like class 2 MLCCs. So it's stable. Those are good things, but the ESR may be a little higher than the MLCC solution, and then the ripple voltage may be a little higher than MLCC solution. And then these parameters like ESR and then DC bias effect, these are available through our KSIM tool. Capacitors also dissipate power, and temperature rise of the capacitor is determined by total power loss multiplied by coefficient of thermal resistance of the component. And power loss is a function of output current and the ESR. And then we have a KSIM tool that shows, that gives you temperature rise versus current. And you can even see, you can even change the frequency, operating frequency, and then you can see the temperature rise for particular part. So if you follow this link, it will show very useful tool. And as conclusion for capacitor, just like inductors, different design constraint or design parameters right here, voltage, frequency, size, and then suitable, there are suitable different solutions available, such as aluminum electrolytic capacitor, polymer, and then ceramics, but there is always trade-off for each. For example, if you wanna, if ESR is important, you want the low ESR, then ceramic might be the best option. However, ceramic does not offer as high a capacitance as the polymer capacitor. So you may have to use multiple MLCCs in series and so on. So takeaway from this presentation is that, there are different passive component technologies available for DC to DC converter, but it's important to know what's the pros, what's the benefits, and then what's the trade-off. And then you can optimize your DC-DC converter design that way. And that will conclude my presentation. Wilmar?
Sorry, I was just looking for my window here. Thank you, Atsuko. I think we're just about at our time limit. And we don't particularly have any questions right now. So I think this is sufficient to, oh, wait a minute. We actually do have a question. The question is, do we provide sample kits by DC to DC architecture? We don't. As far as I know, we don't provide them specifically by DC to DC architecture, whether buck or boost or flyback or, what have you. But perhaps that might not be a bad idea. I think we'll take that and maybe consider that. But thank you for the question. Yeah, the follow-up to the question was also, maybe specific to regulator IC vendor part number and things like that. Yeah, I think that's perhaps something for us to take back and consider. So thank you for that.
Yeah.
So if there are any other questions, maybe we'll give a couple minute or so, and if there are no others, then we'll conclude this particular session of our Design It Day presentation. So it looks like we're not getting any questions, and people are dropping off. So we'll call this one complete, and we'll see you at one of our next Design It Day sessions. So thank you very much, and thank you, Atsu.
Thank you.
Bye-bye.
Bye.